All right, today we're going to dive into a really critical part of machine learning, model evaluation. Because, let's be real, if you can't measure how good your model is, you've just got a black box. We're going to pull back the curtain on the metrics that separate the models that actually work from the ones that are just, well, faking it. Let's get into it.
So let me start by asking you a question. Imagine you have an AI tool that screens for cancer, and it boasts 99% accuracy. I mean, on the surface, that sounds amazing, right? Almost perfect. But is it really good enough? This one question right here gets to the absolute heart of why we have to look beyond a simple accuracy score. And here's why. A model's performance can be incredibly deceptive. It can post these amazing-looking accuracy numbers, but in reality, be completely useless, or, in a high-stakes field like medicine, actually dangerous. You see, training the model is just step one. The real challenge is proving it actually works where it matters. Let's start with the one metric everybody knows: accuracy. It's the most intuitive one, isn't it? It just asks a simple question. Out of all the guesses the model made, how many did it get right? It's a simple percentage, and it feels like the most obvious way to see if a model is any good.
So let's picture this. We build a spam filter, we run a test, and the result comes back 95% accuracy. Your first reaction is probably, awesome, we're done, let's ship it. It's catching almost all the emails correctly. But this is exactly where things get tricky, and where the numbers can lie to you.
The truth is that 95% accuracy score could be hiding a model that is completely, utterly broken. How is that possible? Well, think about your own inbox. What if 95% of all your emails aren't spam? A really lazy model could just predict not spam for every single email, 100% of the time. It wouldn't catch a single spam message, but hey, it would still be right 95% of the time, earning that fantastic-looking accuracy score.
And that, right there, perfectly illustrates the problem. When you have an imbalanced data set, where one outcome is way more common than the other, like not spam or no disease, accuracy becomes what we call a vanity metric. It looks good, but it doesn't tell you the real story. So clearly, we need some better tools for the job. And those better tools all start with something called the confusion matrix. Now, I know, it sounds a little intimidating, but trust me, it's actually a really simple and powerful idea. It's the foundation for understanding every other metric we're about to talk about. So this grid, the confusion matrix, just lays out every possible result in a really clean way. For any prediction, only 4 things can happen. The rows show us what was actually true, reality, and the columns show what our model thought was true, its prediction. Getting a handle on this little 4-box grid is the key to everything else.
Okay, let's break them down. True positives and true negatives, those are the easy ones. That's when your model nailed it, got the answer right. Where it gets really interesting is in the errors. A false positive is basically a false alarm. The model yelled yes when the answer was actually no. And a false negative is a misdetection. The model said nope, nothing here, when it absolutely should have said yes. These 4 little values are the building blocks for everything that comes next.
Okay, so now that we have those 4 outcomes, we can build up to the 2 most important metrics in the game: precision and recall. And to really get a feel for them, we're going to frame this as the doctor's dilemma, where the stakes couldn't possibly be higher.
First up, we've got precision. Precision answers a very specific question. When my model predicts something is positive, how often is it actually right? The main goal when you're focusing on precision is to avoid those false positives, those false alarms. You want to be really sure that when it raises a flag, it means it.
So when does this really matter? Well, think back to that spam filter. You do not want an important email from your client or your boss getting thrown in the spam folder by mistake. That's a false alarm with a high cost. It's the same with credit card fraud detection. You don't want to block a customer's legitimate purchase and frustrate them. In cases like these, you absolutely want to prioritize precision.
Now, on the other side of that coin, we have recall. Recall asks a totally different but equally important question. Of all the positive cases that actually exist out there, how many did my model manage to find? The goal with high recall is to avoid false negatives. You want to make sure you catch everything, leaving nothing behind. And this is where the stakes can be life or death. For cancer screening, missing a case, a false negative, could be a disaster. Same goes for a security system at an airport that fails to spot a threat. In these scenarios, you absolutely have to prioritize recall. You need to find every single positive case, even if it means you get a few more false alarms along the way. And this brings us to the fundamental tension, the real trade-off in model evaluation. Here it is. Improving precision usually hurts recall, and improving recall usually hurts precision. It's a balancing act.
If you make your model super cautious to avoid any false alarms, that's high precision, it's going to get timid and miss some of the real positive cases. On the flip side, if you tell it to catch absolutely everything, that's high recall, it's going to get overeager and cry wolf more often with false alarms.
So let's circle all the way back to our cancer screening tool. Which mistake is worse? A false alarm, which means a healthy patient gets some extra stressful tests but is ultimately okay? Or a missed diagnosis, where a person who actually has cancer is told that they're perfectly fine? Yeah, when you put it that way, the right choice becomes pretty clear, doesn't it?
But what if you can't just pick one? What if both kinds of errors, false alarms, and missed cases are really bad? Well, that's where we need a smarter metric, one that's specifically designed to find that sweet spot, that perfect balance between the two.
And that brings us to the F1 score. Now, the math behind it is called a harmonic mean, but you don't really need to worry about that. All you need to know is that it's a clever way of averaging precision and recall that really punishes extreme unbalanced scores. It combines both of them into one single number, which gives you a much better overall sense of the model's performance. The F1 score is a total game changer for those imbalanced data sets we were talking about, like finding a very rare disease. It's so useful because it severely punishes models that try to cheat by having, say, amazing precision but terrible recall, or the other way around. This makes it a much more honest and robust way to measure how a model is doing in a lot of real-world situations.
Okay, so as we start to wrap this up, I really want to leave you with one big idea. Choosing your evaluation metric isn't just some dry technical step in the process. It's a strategic decision. It's about deciding what kind of mistakes you're willing to live with.
So here it is, all in one place. Accuracy is fine for balanced data sets, where the stakes are low. Precision is your go-to when a false alarm would be a huge pain, like in spam or fraud detection. Recall is non-negotiable when missing something would be dangerous, like in medicine or security. And the F1 score? That's your best friend when you need a smart balance between the two, especially with imbalanced data.
And this is the most important part. The context of your problem is what defines success. Before you even think about the math, you have to ask the human questions. What's the real-world cost of a false alarm, and what's the real-world cost of a missed case? The answer to that is what tells you which metric to use.
Which brings us to the final and I think the most powerful takeaway from all of this. A truly great machine learning model isn't just the one with the highest accuracy. A great model is the one that's been carefully and thoughtfully built to make the right kind of mistakes for the job it's designed to do.